Okay, right. So anyway, so we're going to primarily talk. This is really a follow-up to Richard's talk last month about switching. In his case, it was the voltage out of an inverter, which probably would have been 150, 200, something like volts. But so the focus of this one is really sort of those sort of voltages of which I've tagged here as mains voltage, but it's really anything in the sort of the order of hundreds of volts. So just a bit of an aside, some definitions. So when we're talking about 12 volts, 3.3, 5 volts, we're actually talking about extra low voltage, which is sort of 0 to 50. Now, these definitions do change country to country just ever so slightly, but sort of 0 to 50 AC and 0 to 110 DC is what's known as E or V, or extra low voltage. And then from that to 1,000 volts is low voltage. And then high voltage really starts at 1,000 volts and above. So mains voltage is therefore by definition called low voltage. That's a surprise to some people because you can read a data sheet and misinterpret what the warnings are. So the thing is, be really careful about understanding the term low voltage. And as I said at the very bottom, you only get electrocuted once. It's not low voltage. Sounds safe, but it's not. So be very careful with it. And that's really what the theme of this presentation is about: how to deal with that when you've got some sort of microcontroller. So from Richard's presentation last month, he basically had a triac with an optocoupler. So the 3.3 volts from the Pi or an Arduino, or whatever it is separated out from the mains on the right hand side with basically a chip which has got 4 legs and 2 are on one side of the chip, 2 are on the other, and quite separated. And so the only connection between the 2 sides is light. And so Richard extracted from his presentation, had this little circuit board, which is really good. So he doesn't have the mains voltage on the same board that the Pi or other things are. But if you look closely at that top right-hand side, you can see that he's using a circuit board with little copper pads. And of course, the separation between them is actually quite small. So while you might have a component that's got all the separation of like the optocoupler, millimeters between, or tens of millimeters, so 10 or 12 millimeters between the input and the output, it's actually really the accumulation of just all the separations. So you've got to be really careful. So I would normally use down the bottom a plain circuit board. These are pre-made boards, with absolutely no copper on it at all, and just form up the tracks with components and pieces of wire. And of course, if you're getting into really what this presentation is about is if you're going to make a printed circuit board, is what separation should you have in the tracks that you've laid up. So if we take a view of a circuit board, the green is the fiberglass or the insulation, and the orange is the copper tracks. So the pathways for a short circuit between, or unexpected conduction of electricity between 2 tracks there's 3 potential pathways. The first one's at the top is by the brown lines through the air. It's physically just that the air breaks down and electrons conduct through the air from one track to the next. The second one down is the red one, which is basically along the surface of the PCB. And the third one in the sort of the yellowy color, orange at the bottom, is actually through the PCB itself, through the material itself, the fiberglass or whatever it's made of. Or more importantly, quite often these boards are porous and they absorb moisture. So it's actually through the water that's actually contained in the board. So anyway, the one at the top is clearance. It's known as the clearance distance. So that's the gap, the shortest path in the air gap between the two tracks. Along the surface of the PCB is known as creepage distance. We'll come back and have a look at a bit more detail of those. So let's have a look at all three of those in sort of somewhat reverse order. So through the material itself, typical PCBs are made of FR4 fiberglass, and so normal boards are say 0.8, 0.6, 0.8, 1.6 mil, and I'm saying anything over half a mil can withstand 3,000 volts. So the material itself is not the problem. That's quite robust, and you typically got a solder mask, which is the which just exposes the copper pads, and that provides a sort of an effective layer to stop moisture getting into the board. It does get around the edges where they've cut the board, but it tends not to have a big effect. And even the solder mask, it's say 0.02 mil thick. That's in the order of thousands of volts. So a PCB itself, the base material is quite adequate for mains voltages. That sort of. And when I talk about mains, I could be talking about single phase, 220 volts, 240, or I could be talking phase to phase for a three-phase system of 415, 440, something like that. And so the PCB material itself is fine. As an insulator, the air, typically you're talking about sort of 1,000 volts per millimeter. Now we can get into discussions about, are we talking about RMS voltage or peak to peak or etc. But if you work on the basis that's 1,000 volts RMS for an AC signal, air has a fairly high breakdown voltage. So the thing to remember here is keep the pads at least say 1 millimeter apart for the air to be a reliable insulator. Now, you quite often think about distances being the hole spacing in a PCB, but don't forget the pads are actually bigger than that. So the spacing between the pads may actually be much less. So again, air is not usually the biggest problem we face. So we need to go on to having a look at the third one, which was this creepage distance. So you can see there I've actually shown at the top the clearance is the shortest path in air, and creepage follows the shape of the PCB, and we can actually use that to our advantage by the way you shape a PCB. So if you come over to the power industry and have a look at get a sort of a feel for what sort of distances, and you can see on the right I'm showing an insulator that would normally be hanging in an overhead power line. And you can see the insulator is made up of moldable glass or ceramic insulators, but each one is specially shaped. The top's smooth so that it actually gets washed in the rain, because it's this build up on the surface that actually is what conducts. So in that case, being outdoors, it gets dirt on there, it gets wet in the rain, so it starts to conduct. So what they've done is made the top self-cleaning, and the bottom is got this long tortuous path of being corrugated. So the actual creepage distance is quite a lot longer than the shortest path, the sort of the air shortest part, or the clearance distance. If you look at the top, you look at the sort of distances they're talking about. 16 millimeters for 1,000 volts. That's radically different than the sort of the 1 millimeter for the air gap. For clearance. So it clearly shows that you've got to pay attention to this creepage distance is probably the thing that dominates your thinking when you're designing something. And you can also see how from a clean insulator to something that's been polluted, the distances increase dramatically. So it's all about where the circuit board is, the environment it's in, how much pollution has covered the board, and how moist the surface is. So let's have a look at that aspect then. So there's some relevant standards, and the takeaway message here that you look at this table, and you can see that different countries have got different standards, and more importantly, in the horizontal rows, the different applications have different standards. So if you are making a commercial product, you've really got to understand the market segment that it's going into to make sure you've picked the right standard. Excuse me a second. So we're going to focus on the top two ones, which are the IPC. Now, IPC is an organisation that puts out standards on how to make connectors and terminations of wire and PCBs, PCB soldering, etc. It's quite a good standard in that it's not only prescriptive, it's quite prescriptive in methods, but it's also it's a standard full of photographs. So it's all about showing good practice as well as what you sort of the fundamental requirements. So we start off with this. We start off by saying, what's the voltage level we're aiming at here? So we pick the class of voltage. So let's suggest that we're going to do a 220 volt single phase mains. We come down this table and we'd pick class 3A would be the class that we're working in. We start with that. The next thing we do is we need to evaluate the sort of level of pollution on the surface of the PCB. So if you've got a plastic box with a rubber seal on the lid, cable glands that are stopping any transfer of air, you're in this pollution degree 1, grade 1, and that's really good. That'll have a big impact. But if you jump down here to level 3, as an example, this is where there's conductive pollution or something on the surface of the board, and it can get humid from time to time. And that would be classically a PC or something like that, where you've got a fan that's blowing air through the enclosure, but it's also sucking in dust, and it's accumulating dust inside the machine. So the classic case, you open up a PC and the motherboard's absolutely covered in dust. It only needs to get humid, and you've now got the environment to actually that surface to start conducting. So potentially you could have a lot of equipment sitting in level 3 classification for pollution. So this is a surface pollution on the surface of the PCB. So with those two in mind, so what I've done here is I've just put some control measures. So good rubber seal. You can have a polluted board, but as long as you don't get moisture condensing on the surface of it, it won't conduct. So things like ventilation and more importantly heating. And if the equipment itself is warm, it won't allow condensation. But of course, if you turn the thing on and off, of course it cools down and then you get condensation. So item 3 about if it's running continuously, it's going to have a much better life and etc. The other thing you can do also is coat the boards with a conformal coating after you've finished it, and you put a protective layer over the top of all the. So this is not the solder mask, and it's not the where you put the lettering, etc. And markings on a board. It's a layer of usually polyethylene, spray on polyethylene after all the soldering's been done. And I made a point at the very bottom about putting filters on fans. That actually doesn't stop the problem. All it does is slows it down a bit, but you still end up with a surface of conductive material on a PCB. So so I've got the image of people up in the middle of the screen. So if we take the previous example of, say, 220 volt class 3A, say pollution degree 2, So we'll come over to this table and you can see down the left-hand side, the working voltage is sort of 200, 250. Pollution degree 2 in the center column here. Come down, it's a class 3A was the voltage. We come down and it's around about 2 mil to 2.5 millimeters spacing. You can do linear interpolation, so 220 volts would be say 2.2 millimeters. But it gives you a sense of it's far more than the 1 millimeter for just the air gap. Now 2.2 mil is just about very close to the 0.1 inch, 2.54 mil hole spacing in a PCB. By the time you put the pads on there, or if you take the case where I had the insulated board with holes in it, you put a triac legs through, and then you wrap some wire around it and solder it. The gap between the pins is actually less than 2.2 mil. So I would typically take something like a triac and spread the legs out into every second hole. So now you're at about a 5 mil spacing. But so you can use this table to actually, and the previous ones, to give you a guide on what sort of spacing you need to apply. So some control measures you can do to increase the creepage distance is put some physical barriers. And on the right hand side, you can see by putting a slot in the board, it means the conduction has got to go the long way around. And that's probably one of the typical ways of increasing the distance, the creepage distance between pads. Another sort of similar view, you can cut grooves in a board, not all the way through. Notice here in the middle, when the V-shaped groove gets less than 1 millimeter, you don't consider the groove anything deeper than that. You cut across at that point. And similarly, a notch, as long as the notch is more than 1 millimeter, you can use that to your advantage. But on the right-hand side, you can see a slot cut right through the board is a typical solution to that. And it's something that a PCB maker can actually do as part of the manufacture of the board. So here's coming back to the first method of, in a sealed enclosure. So here's an optocoupler at the top. You can see the resistor right on the top of the in-series resistor in series with a lead. Coming off a PIC controller. It's running an opto. There's a triac for mains, etc. There's no tracks on this board. It's a purely, hand soldered job. And as I said, that's been in operation for 23 years and running the garden lights. And you can see there's nothing on that circuit board. It's absolutely clean. So I went for a really high quality industrial plastic enclosure with a good seal. And the sidewalls of the enclosure are quite deep, so that you don't get the lid flexing and the seal breaking after a while. So that's one method, and that works really effectively. So the next aspect of this whole issue is also how do you keep. So coming back to here, you can see I've physically got the extra low voltage, the 5 volts at this end, and the mains down at this end. So I've also segregated the layout of this board, and you can see Richard's board last month was the same. The signals from the pi at one end of the board and the mains at the other. So segregation is a follow-on aspect of keeping these two separate. So there's a fundamental rule that says if you have extra low voltage and low voltage in the same and the terminals in the same enclosure, you actually need to insulate everything to the highest voltage. So it would mean all your insulation, all your wiring and everything would have to be at mains voltage levels. So that's quite often not practical. So you've then got to think about how can you work around that. So the rule is, to give you an example, in telecoms, you must never pass the mains down the telephone or the internet lines. So what you quite often do is you need a physical barrier inside the enclosure to separate, actually to create effectively two enclosures. So to get around this problem of everything must be insulated to the highest voltage. And I'm also making the point the same rule applies inside the relays and any other device that you've got. So things like optocouplers do that, but relays, not every relay would meet that requirement. So with segregation, what we're doing is here, we're designing for failure. You ask yourself the question, Richard had the DC on one end into a screw terminal and the mains on the other. The question would be, what happens if one of the mains wires came out of the screw terminal and was left floating around inside the cabinet? What could it touch? And the same applies inside things like relays. What if the coil wire broke? What could it touch if it came loose? And so quite often you'll think about how do I cable tie the wires down? How do I restrain them so that even if they do come loose, they can't accidentally touch, the mains can't touch the E or V type wiring. And so it becomes an issue about how you lay out the wiring inside a cabinet, how you restrain it, etc. So it's quite often in this day and age, segregation is not obvious because we quite often use plug pack power supplies, and that the manufacturer of that's taking everything into account. They've dealt with all those issues and solved it for us. And so we don't tend to think about segregation all that much these days. However, if you've got a mains voltage on a PCB, you've actually got to think about this again. So there's other aspects to do. You could say, okay, well, I can either design it myself. I could use a third-party device where I put an extra low voltage signal on one side and it switches the mains for me, and it's actually an approved device. I could use something like a radio switch, so you could buy a third-party plug pack that goes in a power outlet, and you plug your device into that, and you signal by Wi-Fi, and you physically got no wiring between mains and ELV. But if you do have to do it yourself, or you want to do it yourself, there's a couple of things to think about. Going back to my example here, on a triac, the tag on the triac is actually connected to the center pin, and that's quite often unswitched active. So that means in this case, this whole heatsink is live. So you need to be very careful with that. So you can actually buy TO220 type triacs and similar, where the heatsink's not live, it's an insulator tab. So you need to deliberately go and select a device like that. You need to add plenty of labels to actually make sure people understand what's live and what's not, and before lay out the board to physically separate the E or V from the low voltage. And the last thing is have a think about putting some covers over it. So you physically got to take a cover off to actually get to the mains part of a board. And that could be, say, a 3D printed cover, which you screw onto physically screw to the PCB, have some holes in the PCB and screw it down. So here's some examples, and I'm normally very cautious about these little blue relays because you can see here on the left-hand side, you've got the contact switching. But the common for the mains is actually right near the E or V terminals. I do get cautious about, you see a lot of people using these in sort of Arduinos and Pis, but they have their traps. However, this one is really good. You can see they've actually cut a slot around to get the creepage distance correct. So there's some really good, like this one, there's some really good ones, and there's also some shockers around. So you need to, even when you're looking at buying this sort of thing, you need to look very carefully at what you're getting. Appropriate relays. In this one, you can see that the contacts are on one side and the coils are on the other, and And don't get trapped with the relay base that you plug it into. You can see here the coil contacts on the left-hand side are on one side of the base, and the contacts are on the other. There are a lot of relay bases around where they actually mix them all together, and you can't get the separation of the wiring. A couple of cases here, you get these solid state relays. You can see this one on the left, they've actually got physical covers over the 240 volt terminals, top end, well, the 240 and the 24 volt terminals. Again, that's really good design, but you need to select them very carefully. And I was talking about relays having barriers in them. You can see this one on the right. You can see the physical, in the plastic molding of the cover, there's actually a physical barrier between the coil and the contacts. That's the sort of thing I'm talking about, just getting the appropriate relays with segregation in them. So the TV industry is actually quite good at this. You can see here a circuit board out of a power supply, out of a television. You can see the white line using the word hot and cold for high voltage or low voltage mains on one side and extra low voltage on the other. And you can see the transformers straddling that line because it's the isolation. There's an optocoupler here straddling the line. And so they've been very careful to make it clearly obvious what's at mains and what's not. And you get another example here. It's abundantly clear what's running at mains voltage, and that's just purely markings on the circuit board. So that's it. I'm going to reference here. This link here is quite a good article on how to design and the aspects of it. And also, we talked with Andrew did a presentation probably a couple of years ago on a circuit board that he had with I think it was with output relays, but it was the aspect of that presentation was good. Was that he thought through clearly about the layout, the physical layout of that board. So and I was talking to Andrew before, you might be able to do a follow-up or repeat of that presentation, or just the aspects of the PCB aspects, in a coming meeting. So that's it. Anybody's got any questions?
Yeah, I had a question, Tony. So it was really good. It's really interesting. I like particularly that picture of the relay. That's one of the questions I had. How do you choose a decent component? But then I was also wondering, how do I know like my meter is good for mains voltage? Just because it says good for mains voltage, it doesn't necessarily mean anything, does it?
As in your multimeter?
Yeah, exactly, multimeter. Imagine some cheap multimeters may not be appropriate for mains.
Yes, maybe Andrew, you can jump in. I can never remember the classes, meter classes that, but they're meter categories, aren't they?
Well, so a lot of the cheap ones will just have, plain test leads. If you're working in an industrial environment where you are expected to stick a multimeter on the mains, it will certainly have things like fused test leads, which, so when you accidentally measure the mains voltage with the test leads plugged into the amps position on the meter, you don't end up with the thing blowing up in an uncontrolled way in your hands. So yeah, that's the sort of, you pay vastly more for a meter that meets that kind of criteria. To answer Tony, I don't remember the classifications for the meters.
There's Cat 3 and Cat 4, I think, for different classes. But to follow on what Andrew's saying about accidentally plugging a meter in on amps and failing, we would normally use meters that have got just a voltmeter. They don't have an amps range. Well, they're actually they're a clamp ammeter, but it means you can't accidentally put it on the wrong range and fail. And the other thing you do is go and plug the meter into a known source, like into an power outlet, and check that it actually shows 240 volts before you start fiddling around, because you're trusting that the meter's working. Now, I use my meter a lot, and just recently I found I'd broken the leads on it, and it's only by going through that process I discovered that it would have shown me 0 volts. I would have thought it's dead, and I would have touched it. I've got this instinctive habit of don't trust anything. I'd like.
There's also a rather horrific film that is around on the internet, which goes through the details of a fatal accident, actually, where a guy was looking after, I think he measured the voltage in some PDUs, power distribution units, in an industrial plant where they had, the typical 240 volt mains. I think it might have been the US actually, but also had the next stage up was like 4,500 volts. Anyway, he wasn't thinking straight one day, measured the 4,500 volts with this test meter that was suitable for 240 volts, and the resulting explosion killed him. So, yeah. You need to he'd been in that plant for years. He knew it inside out. He knew which PDUs had which voltage, but he still made that mistake. So.
Yeah. And one of the things we didn't talk about is fault current. Actually, that brings up a good point. If you're next to a transformer, really close to a transformer in an industrial, well, no, even in a housing environment, say it's a 1 megawatt, 1 MVA transformer, you get a short circuit current of in excess of 20,000 amps. Short circuits phase to earth, phase to neutral. That's quite high. So people will take mains voltage equipment and say, "Oh, put a fuse in it," and they take a little glass, auto fuse that typically they use in a car or something. You want to see it vaporize. You want to see the fuse holder vaporize under those conditions. So you need to be also thinking about, you need typically it's a ceramic fuse. It's in the same shape and all that, these like little bullet fuses, but they're a high rupture capacity. So inside the ceramic is sand, and the elements actually so actually as it fails, the sand catches or absorbs the heat, and the fuse works in a controlled way. But don't expect a small glass fuse to actually protect you. It can actually do more damage than it sets out to protect.
I came across an interesting example of breakdown many years ago. We had an electromagnet which operated at 2 kV, about 4 or 5 amps. And there was a reversing switch on the power supply because we sometimes wanted to change the direction of the field. And the magnet became unstable. So we opened the power supply and found the reversing switch was rated at 250 volts. There was a nice carbon track running outside it.
Yeah.
We did tell the manufacturers.
Tony,
Yeah.
I have a question, and it's not actually about big voltages. It's actually the return path and earthing. So I've got a normally your 240 volts in the UK has your live, your neutral, and your earth. But in your sort of, your 5 volts and Arduino sort of circuits, you've just got your supply and ground. It's known as. Yeah. When you mix them up onto in an enclosure, which you can have metal enclosures, and a lot of the time you're supposed to bond and earth everything. Is the ground effectively the same as the earth? So your 5 volt ground circuit, should you be bonding that to your 240 earth? Because that feels like you're got big boulders of 240 volts and tiny little pebbles of 5 volt earthing and ground. And I just wonder how you think you should bond systems in enclosures with various voltages.
Okay, so this doesn't really matter what voltage you're talking about. As soon as you go through a transformer, 2 systems are independent. So if you go down to the your local substation, your nearest substation feeding your house, and it's got, say, 11 kV or 22 kV or something like that, 66 kV coming into that substation, that system is quite different and it's quite separate than the earth. You know, I'm talking about the earthing and the return paths. If you had a phase to earth fault on the 66 kV, it will go back to the current will go back through the earth or back through the cabling or whatever, back to the source. And same with the 11 kV. So that while they might all be bonded to the same earth, and the same would apply to a 5-volt supply, they might all be bonded to the same, you know, what you might call earth or 0 point. They're actually all independent of each other. And that's the very point of having transformers and optocouplers and all that. So what you, in fact, earlier in my career, I used to work as a protection engineer doing 66 and 11 kV protection design. So the thing that was always drummed into me is, draw me the circuit. Yeah, okay, I've got a 5-volt supply, and I've accidentally shorted it to the 0-volt line. Okay, draw me the circuit, and you'll say, oh, it comes out of the 5-volt power supply, goes down this wire, down through this short circuit I've accidentally done, and it comes back, and you can draw the loop. Just because one of those points in that somewhere in that loop was hooked to say 0 volts, which happened to be the same as the mains earth, the current physical electrons don't leave that circuit. They don't end up, you know, mysteriously ending up in the 240 volt circuit or elsewhere. So you've got to think about these things. If you've got transformer isolation, you've got to think, you can think about these things quite separate to each other. Now, you can leave the 5-volt floating, if you like. You know, the output of a got one here, like a Raspberry Pi 5-volt transformer. It's got, you know, 2 output wires, you know, 0 and 5. That they are just floating above, you know, in terms of respect to Earth. You know, like, you know, an Earth stake in the ground. They're floating and they're fine. You don't need to bond them to 0. It's only when you're starting to talk about long cables and interference and radio signals getting picked up in wires and causing interference that you start talking about that sort of thing.
So, sorry. In summary, you keep your ground of your 5-volt separate to your earth, and earth your 240 volts as you would, even though your 5 volts is mounted on that.
So behind your wall socket, there's a set of regulations that say what the connection is between the earth pin on the wall socket and the neutral pin, and there'll be some connection between the two, probably in your switchboard or back in the street somewhere, but that's highly regulated. So you don't start making connections between neutral and earth in your equipment.
Oh no, I'm not saying that. No. So that side's highly regulated. When you get to ELV, you can do what you like. You're not legally obliged to start connecting certain things to other things. That's the advantage of ELV. You can just let it be what you want it to be. You're not forced or regulated to do things.
Yeah, I was going to throw a thought in there, because this is something I thought about, where you've got, you know, an example, if you've got 5 or 12 volts ELV, you know, driving some of the kit, for example, driving relays that's switching mains. You could leave it all floating. I don't. I ground it, and the reason for that is I've usually got that extra low voltage, you know, strung across, you know, bell wire type. Well, no, it's not really bell wire, but not mains cable. And if something did happen in my enclosure and that became live, I don't want that all floating at 240 volts.
Yeah.
So by grounding it, something's going to go bang, and I'm going to know that it's gone wrong, rather than just having 240 volts on bell wire across the house. So that's my thought on that one.
Yeah. So what Andrew is talking about is absolutely correct. So the reason that you have this concept of an earth wire in your socket outlet on your wall, and it's connected to, say, the metal chassis of a piece of equipment like a PC, is that when that wire accidentally the active wire accidentally does come off something and touches the case, you've got this circuit back which will blow the fuse.
Yeah.
So what Andrew's talking about is exactly the same thing. If it accidentally got off and touched the piece of bell wire and got into your pi circuit, you've created a pathway back to in the main circuit that will cause a large current. Yes, it will cause a failure, but it also will blow the fuse or blow the breaker. So it's absolutely a good practice, but it's not regulated.
Thank you very much, guys.
So
Tony.
put it this way, if I've got a little enclosure where I've got nothing, it's just a pi and a switch next to it, I probably would let it float. But as Andrew's saying, as soon as you start running wiring out, the exposure changes dramatically, and you run the risk of things accidentally happening. Wire gets cut, etc. So in those cases, I would absolutely ground it in those cases.
So the ground of your pi connected to the earth.
Just the 0 volt of the power supply, the pi's power supply.
Yeah.
Just to 0 volt, to earth, yeah.
Thank you very much.
There's a lot of regulation in the UK on that about metal enclosures, and that if you've got mains going into a metal enclosure, the metal needs to be linked to the earth of the mains plug, but you wouldn't let that go anywhere near the extra low voltage side of your circuit.
So
Tony,
you'll see a lot of power supplies are double insulated. If a power supply's got this double square symbol, it tells you that the thing is double insulated, and they've taken a lot of care in the design of that.
So it's Brian here, but just to add to that, your earth on your pi, and if you have a separate power supply, let's say running, like I have running a LED strip, you would want to earth 5 volts on your power supply to the earth on your Raspberry Pi, for instance. So that's where you would have a common earth. Otherwise, actually, the LED strip it's very temperamental. But you never take that earth back to your neutral or earth on the main side. But you would link them from the power supply earth to your earth on your Raspberry Pi. Does that make sense?
I think there's a lot of use of the word earth where it's not earth.
I know.
You're using the word basically it's common or ground, but
ground, yes, maybe. Yeah.
But on your mains it's earth.
They're terrible, and if you cross the Atlantic, you connect the ground to the earth, and on this side you connect the earth to the ground. They mean the same thing.
So one of the important things to think about, people get hung up about, I've got to go and get a stake, a metal stake, and drive it into the soil outside. It's not what it's about. The real term is equipotential bonding. It's about getting everything connected together.
Yeah.
So the metal on the PC case is hooked to the same metal as your sink.
Yeah.
There's
no potential difference. Make sure there's no potential difference.
Absolutely. So you can touch a kettle and the sink, and you don't get a voltage difference when.
Yeah. Sorry, just on that, I was talking about the earth side, negative, whatever you want to call it. But on the actual positive side, you don't want to link let's say one of your positive GPIO 5 volt pins to the 5 volt on your power supply, because apparently that can give a problem. So I've got like a switching supply that goes into my LED strips. So the whatever we're calling now, negative earth, whatever, that is linked, but the positive should not be. Otherwise, you get a backfeed through the GPIO pins of 5 volts, and you're not going through the fuse that is on the USB power supply to the Raspberry Pi. So backfeeding that power apparently is not a good idea. Does that make sense?
Yeah, I mean, if you supply the Pi through the GPIO pins, not through the power pins on the GPIO pins, there's no protection against.
Yeah, that's what I mean. Yeah, exactly. So that's why you wouldn't link those, but the earth you would. But yeah, the power, it's better to go through the USB if you want that protection, unless you're absolutely sure about your power supply, of course.
Yeah. I think a simple way to think about this is don't worry about the Pi and all the peripherals. Think about the power supply itself. you've got a 5-volt little, say, a power pack, and one with me. You know, one of these like mean world type. There's a little block, put mains in one side, active, neutral, and you put earth to say the metal case, and you've got 0 and 5 coming out the other side. You might link what Andrew's talking about. You might link the 0 of that power supply to earth as well. You're not talking about doing anything over on the Pi or on the GPIO. It's back at the power supply. And you put one bond in, one connection in, not multiple, because you end up forming up loops and interference will happen. But you put it between the 0 volt of the power supply and say earth. 1 point only.
Thanks very much.
I have a question about the definition of ELV.
Yeah.
Can I ask you about the definition of ELV?
Yeah.
I was surprised to see 110 volts is classed as ELV. There's a common 50 volt suggested limit for public use. Do you know where that comes from and what the criteria are for a project to have to adhere to that?
So when I was saying 110, it was 110 DC, not AC.
Yes.
I don't know where the 50. I've seen it move. I've seen this number. So over, I'll start to show my age now. Over the last 20 or so years, I've seen this number move around a bit, and I think it's probably more aligning as countries start to align together and common up standards. I don't know the background of that, but the bottom line is you can get electric shock and die, get electrocuted if you like from a 9-volt battery. You do something, you're unfortunate, and where you in a situation you get yourself into it. But these are sort of commonly accepted safe limits.
So my application is I'm thinking of providing public charging for electric bikes. And my understanding was that you shouldn't provide above 50 volts DC in the public sphere.
I have a real interest in electric vehicles at the moment, and looking at actually building product. One of the things that and I don't know about how the bikes work, but what cars do is they've got a couple of control pins on the plug, and it's not until you've actually plugged the plug into the vehicle and there's some handshaking between the two that the voltage, the charging voltage, is applied to the vehicle and via the cable and plug. So people are not exposed to high voltage, or like low voltage 200, 400 volts. Some of them will charge at say 400 volt DC, others will do 415 3-phase AC. None of that's exposed until the vehicle and the charger are communicating with each other. So you might find you can get yourself out of that problem with that method.
I guess it depends. Are you talking about electric motorbikes, or are you talking about the kind of things that power-assisted pedal cycles? Yeah, the latter. Yeah, but the power-assisted pedal cycles are generally kind of 24, 48 volt batteries, whereas the proper bikes are higher voltage and will have a proper AC kind of converter, whereas the pedal bikes don't. So yeah, your challenge is a bit different there. But what Tony said is spot on regarding EVs. They use the two control pins to negotiate, and then there's a contactor actually in the charger that engages when it detects a correct handshake. Yeah, I was trying to look into the feasibility of a very simple low-cost system that could be more ubiquitous than the normal charging. And for pedal cycles, the common voltages these days are
still 36, but also 48 and 52. And with the range of voltage that batteries produce as they discharge and then recharge, that takes you up to about 60 volts.
Yep.
So that hence the question: can you hang 60 volts on a lamppost, or will somebody not be pleased?
You're going to need suitable protection anyway. So
yeah, I mean, there's a number of ways you can do it, because chargers at the moment, even just on a sort of a normal battery pack, will do voltage detection to then detect if there's a battery connected before they then supply the power.
Yeah, and to follow on to that, you quite often need to do voltage reversal to check that you haven't plugged it in backwards, or the bike's got a battery installed backwards. So you do two things. You look for voltage reversal and then voltage level, and the charger would switch into the right voltage level. We do that quite often with forklifts, single charges for multiple forklifts.
Guys,
you're looking at that 110 volts as well. It's defined as ripple free DC, so it can't. It actually has to be really smooth DC to go to the 110 volts.
Yeah. Sorry, guys, we're gonna have to move on. Thanks, Tony. That was really good. Prompted a lot of discussion there. Hopefully everyone stays safe. There's some good links in the some links in the chat. You guys may want to check that out. Thanks, Tony.
Yeah, no problem.
It's good observability for us.